Oh, the banked road, no friction. It's exciting. So this scenario is the car is going around a banked road. I drew in its taillights so you could see that this would be like the path it's going. The car is going away from me. So it's not going up the hill this way. The car is going around the corner. Think NASCAR. And they have those steep banked roads, right? So they do that. So the normal is the thing that makes that circle happen. So we get more than normal. So those are some pretty steep roads. And it's the same kind of thing going on here. So we want the car to be able to go 50 kilometers an hour per hour around this turn with a radius equals 50 meters. And the engineers designing this road, they want you to do it to where there is no friction, so that friction isn't needed. Friction not needed. And you think, you know, like in terms of NASCAR, where they're doing circles all day long. You know, having friction not needed and the normal being the thing that's making you go, kind of go around the inside of a pie tin is handy. So it just takes out some of the guesswork. So we want to know how high that angle needs to be. So let's just draw on there. What's kind of nice is this force gravity is straight down. And the force normal is straight up. Oh. So I look at that and I ask myself, well, what's going on here? So I'm going to have something that's keeping me from flying up into the air or plummeting down to the earth. And I think what is easier this time, because we don't have any other forces, is that if we do this, and I leave gravity on my axes, and now I have a y component of the normal. So here's my normal, so it's going to have some sort of y component, equal and opposite for the gravity, so that's the not flying up or falling down. That would be my F normal in the y. And then what's my center seeking piece? Wouldn't it just be that thing pointing towards the center of the circle, which would be over here? And indeed it would. So the force normal in the x is the thing that is I'm pushing against to make the turn. So the force gravity now is all on axes. And what do I get? I am going to remind myself that my acceleration is that away. And so my center seeking force, so let's just do to the right and up as positive. Let's do my sum now. I need pens. So my sum of forces in the y, we'll just go ahead and start there. So just as the gravity, the angle between gravity and the normal is the angle of the incline, the angle between here, the normal and gravity, excuse me, will also be the angle of the incline. So you can see these are kind of like equal and opposite. They're just intersecting lines. So I have, let's say, force normal in the y. So force normal is touching that line. Force normal cosine of theta minus mg. And that's not flying up in the air or falling down, so that equals 0. So my force normal cosine theta equals mg. Now I'm going to do something here because it's asking me to solve for how much of an incline that needs to be. So just on a hunch, I'm going to go ahead and solve for the force normal. So the force normal equals mg divided by cosine of theta. There. So I'll stop there. Now let's look at my x, or my center seeking force in the x. Then, see, my acceleration is this way. I've defined that way as positive. So it's the force normal in the x, force normal sine of theta equals mv squared over r. This is my center seeking force. That is the thing pointing towards the center of the radius of this circle. So it's that force normal that's making that happen. So as I looked over here, I'm like, okay, so let's get rid of that force normal. We'll do the same thing here. Do the same thing here. I'm just going to move that sine theta to the other side. So I get force normal equals mv squared over sine theta r. Cool. It wanted me to solve for an angle. So let's go ahead and set these two normals equal to each other, because remember, that's what these are. These are the resultant normal. That's that. So this is totally legit. So now I can go mg over cosine theta equals mv squared over sine theta times r. Ooh. Now I want something. Let's move this on up here. And how did my hair get there? All right. So I can look at this. Let's simplify this before I rewrite anything. My m's will cancel out. And I see trig functions. Whenever I see trig functions, I like to remind myself of one of the happiest trig functions on the face of the earth, next to the ones that you will use at some point in life, tan theta. Why do I want that? Because these are two trig functions. I need to solve for an angle. So solving for an angle with two unknowns, well, one unknown, but two functions, is really hard to do. You can't do it, right? We don't have enough equations to start getting rid of a sine or a cosine. So this, as soon as you see this, if I can put sine over cosine, I'm going to do that. So I'm going to rewrite this as sine theta over cosine theta. So I've done this, I've moved this up here, equals v squared over r. That's just this piece. I need that g gone, so I'm going to move the g down over here. So I can rewrite this as tan theta equals v squared over gr. Yep. Or if I take the arctan of both sides, that leaves me with theta equals the arctangent of v squared over gr. So taking the arctangent, if you kind of look at this, arctan times tan, well, that makes the trig function go away and leaves me just with this. So doing it to both sides of the equation is totally legit. And that means that taking the arctan of this gives me my final answer. So now I can put numbers in there. What do I have? I have kilometers per hour. Oh, now I'm sad. I have to do some conversions here. Let's do something, shall we? Let's practice a little bit with using the web. Convert kilometers per hour to meters per second. Why not? So my kilometers per hour are 50, and that gives me 13.88. So this is 13.89 meters per second. Cool. At this point in time, a point and a quarter, I expect that you guys can do these conversions, so I don't expect you to show me that kind of conversion. If you have it in your phone and you can do that, that's fine. If you can do it on the computer, that's fine. All right, so we have arctan of v squared 13.89 squared divided by 9.8 becomes the radius of the circle, which is 50 meters. Oh, no units, sorry. Now put that in the calculator. So I have 13.89 squared divided by 9.8 times 50. I'm going to take the arctan of that. So arctan of that gives me 21.49 degrees. And I'm done. So at this angle, with no friction, my car will stay on the incline. Kind of cool. there you go. We are done with all these examples.